Okay, more goofing around on the guitar as usual. I don't know what in the world that was either. Had some sort of a Native American kind of feel to it, so that was kind of interesting. So let's see, we're going to go ahead and we'll be looking at 3.3 today. So beginning with this, we're going to learn a little bit about two different identities. This is actually a pretty short section. We've got cosine sum and cosine difference identity. So there's a certain structure to this, and you want to memorize this. So one of the first things I want you to notice, if you're doing the cosine of the sum of two angles, the identity has a difference in it. And if you're doing the cosine of a difference, the identity has a sum in it. So I always try to look at the structure kind of like this. The cosine of the sum goes cosine, cosine, sine, sine, difference sine. Same thing with the cosine difference. Cosine, cosine, sine, sine, difference sine. Okay? So get a little bit of the musical rhythm going. One of the things that we use these identities for is, like, for instance, if we had something like the cosine of 75 degrees on a unit circle, 75 degrees is not one of those angles that is derived from special triangles that use a 30, 45, and 60 degree angle. So we can use the cosine sum identity and difference identities to find more angles that we could add to the unit circle that would give us exact values. Okay? Theoretically, every single angle is on the unit circle, but we only kind of draw the unit circle for special angles that are derived from either quadrantal angles or from the special triangles. So what we could do is, like, if you had a 75 degree angle, you could write that as 45 degrees plus 30 degrees, and then you could use this identity for the cosine sum. If you had a 15 degree angle, you could use 45 degrees minus 30 degrees, or you could use maybe 60 degrees minus 45 degrees, and you could use the cosine difference angle if you wanted to then. Okay? And then think about if you had like 105 degrees, well, you could do this if you wanted to. You could do 60 degrees plus 45 degrees, and that would allow you to use the cosine sum identity when you did that then. Okay, so what we're going to do is learn how to use these identities. So let's start with cosine of 5 pi over 12. First of all, let's convert this to degrees just to kind of see where we're at. So if we have 5 times 180 degrees over 12, and if we just crunch that on the calculator, we'd have 5 times 180 divided by 12 by my calculations is giving me 75 degrees. Okay, so we get a 75 degree angle, which tells us that you're in quadrant 1. And we know the cosine of a quadrant 1 angle is positive, as all trig functions are positive, give positive values in quadrant 1. So what we're going to do is we're going to use the identity. So let's start by writing down the cosine of 75 degrees. And let's go ahead and break this one up like this. Let's write this as the cosine of 45 degrees plus 30 degrees. Okay, then we're going to utilize our identity. So the identity for the cosine of a sum of two angles goes like this. You do the cosine of the first angle times the cosine of the second angle. Then you change the sign. It's a different sign than the plus. And then you do the sine of both angles. So you do the sine of 45 degrees times the sine of 30 degrees. Okay, so again, the structure goes cosine, cosine, sine, sine, difference sine. Okay, now let's look at a couple of things on a unit circle. So I'll draw a unit circle diagram just kind of at the side here. And we're going to be interested in a 30 degree angle and a 45 degree angle. So at 30 degrees on the unit circle, we have the point square root of 3 over 2, 1/2. And at 45 degrees on the unit circle, we have a point square root of 2 over 2, square root of 2 over 2. So we're going to utilize these things basically to work this out. So the cosine of 45 degrees, of course, is the x value. So that's going to be square root of 2 over 2. And the cosine of 30 degrees is going to be the x value again. So that is going to be the square root of 3 over 2. Okay. Then we want to find the sine of 45 degrees. So that is the y value of that point, which is going to be square root of 2 over 2. And then we want to find the sine of 30 degrees, which is going to be the y value. So that is 1/2. Okay, so now we're just going to crunch out the details. So if you multiply this fraction straight across, you're going to get square root of 6 over 4. If you multiply this straight across, you're going to get square root of 2 over 4. So then you would get a final answer to the problem, which would be square root of 6 minus square root of 2 all over 4. And that's a precise answer to that problem. Okay. Now, one of the things I'm saying that you can do on these problems frequently is you can check on your calculator. So I'm going to pull up my trusty calculator and going to do a couple things on this. So first of all, let's go to radian mode. Since the problem was given in radians, let's do the cosine of 5 pi over 12. That's the problem you were asked to find the exact value of. And of course, the calculator is going to give you an approximate answer. Now, if you take our answer, and you'd have to do the numerator in parentheses, so you'd do square root of 6 minus square root of 2. Notice how I use the parentheses on that, then divide by 4, and you'll get precisely the same answer. So what we have developed is by using this identity, we have an exact answer to the cosine of 75 degrees. Okay, like that. And again, you can check with your calculator. Okay, moving on to the next example. We want to look at the cosine of 345 degrees. Okay, well, first of all, this, of course, is a quadrant 4 angle. The cosine is positive in quadrant 4. Remember, the cosine is positive where x is positive, so that's quadrant 1 and quadrant 4. So the first challenge is to figure out, can we think of two angles that we use on the unit circle that could add or subtract to give 345. Now, what comes to mind for me, and there's more than one way to do this, is 300 degrees is on the unit circle, as is 45 degrees. So we're going to use the cosine sum angle again to do this. So I'm going to do this like this. Okay, this identity says cosine of the first angle times the cosine of the second angle. Okay, then you do a different sign. Then you do the sine of the first angle. And you multiply that by the sine of the second angle. Okay, like that. All right, so again, the structure is cosine, cosine, sine, sine, different sine. Like that, okay? Now what we're going to do is we're going to pull out a unit circle and we're going to figure out the values from the unit circle. So we need to really look at two things here. We need to look at a 45 degree angle, of course, on the unit circle. 45 degree angle has the point square root of 2 over 2, square root of 2 over 2. So we're going to utilize that. And then a 300 degree angle is going to be actually this angle. And on the unit circle, that corresponds to the point 1/2 for x and negative square root of 3 over 2 for y. So what we're going to do is we're going to start by finding the cosine of 300 degrees is the x value. So that is 1/2. Then we're going to look at the cosine of 45 degrees, which is the x value again. So that is going to work out to be square root of 2 over 2. And just following the identity, we have a subtraction symbol. Then we're going to do the sine of 300 degrees, which is the y value on the unit circle. So that is going to be negative square root of 3 over 2. Then we're going to look at the sine of 45 degrees on a unit circle, which is square root of 2 over 2. Okay, so we multiply this out straight across. That's going to be square root of 2 over 4. This is going to be, now notice on this you have a minus, and then this is going to be negative square root of 6 over 4. So then subtracting a negative is the same thing as adding, so we get square root of 2 over 4 added to square root of 6 over 4. So we can put this in one fraction to get the answer of square root of 2 plus square root of 6 all over 4. Okay, and then that would be the precise answer to the cosine of 345 degrees. Okay, right? Now notice we were in quadrant 4. We got a positive answer. You can tell by looking at this answer that's positive. We could also check this on a calculator. So I'm going to put my calculator in degree mode this time. And I'm going to do two things. I'm going to do the cosine of 345 degrees, which is giving me a positive answer. Then if I take our answer, and notice how I do the parentheses, I got to do the numerator in its own set of parentheses. So I'm going to do this like this. Got to double up on those parentheses. Not triple up on them, Brad. Double up on it. Okay, so we go like that. Then divide by 4. And we get precisely the same answer. So again, checkable on the calculator. All right, so that's how you use the cosine identity. All right, now I will let you all try to do a problem number 3 just using the cosine identity. Okay, so let's take a look at what you should have come up with. Now, first of all, with this problem, of course, the first thing you want to pay attention to is you are in quadrant 2. So we would expect to get a negative answer. Again, the cosine is negative where x is negative. So it's negative in quadrants 2 and quadrants 3. There's several ways you could have done this. I think the way I'm going to do this is I'm going to do cosine of 120 degrees plus 45 degrees. Okay, that's one way to do it. I'm sure there's other ways to do it too. That's just what comes to my mind when you do that. All right, so I'm going to do this like this. So the identity goes cosine of the first angle times the cosine of the second angle. Different signs, so we're going to do minus, and then we do the sine of the first angle times the sine of the second angle. Then we just need to consider what's going on the unit circle. Okay, so let me draw a unit circle diagram to the side here. Okay, so first thing is 45 degrees. Okay, we know we have 30, 45, and 60. So at 45 degrees, we have the point square root of 2 over 2, square root of 2 over 2. And then 120 degrees is quadrant 2. And that one would actually be this angle right here. So 120 degrees would be this angle. And on the unit circle, that corresponds to the point negative 1/2 and square root of 3 over 2. All right, so we're ready to put this together. The cosine of 120 is the x value at that point. So that would be negative 1/2. The cosine of 45 degrees is the x value at this point. So that's going to be times square root of 2 over 2, and bring down the minus sign. And the sine of 120 degrees is square root of 3 over 2. And the sine of 45 degrees is the y value, so that is also square root of 2 over 2. Okay, so what we're going to get when we multiply this out, this is going to be negative square root of 2 over 4 minus square root of 6 over 4, like that. Okay, and then what we're going to have is, when we put this together, we've got the common denominator, combine the numerator, so we would get this as the answer of the problem. And you can tell clearly that's a negative answer that we expected we would get. Okay, remember we expected to get a negative answer. If you want to take a minute to check this on the calculator, this would go like this. So if we do cosine of 165, that's going to give a negative answer. Calculator does not lie. And then we're going to do parentheses negative square root of 2 minus square root of 6 aroo. Close parentheses, divide by 4, voila, we get the same answer. Isn't that amazing? Okay, so that would be the solution of the problem. That's one way to do the problem. There's other ways as well. Okay, now we're going to look at the next page we're going to look basically just at the identities in reverse. So one of the things I want to write down on here is like if you have a cosine of alpha plus beta, the identity goes like this. It goes cosine alpha, cosine beta, different sine, sine alpha, sine beta. And then if you have the cosine of alpha minus beta, that goes like this. It goes cosine alpha, cosine beta, different sine, sine alpha, sine beta. I always try to get rhythm going because it helps you remember this stuff for whatever reason. So again, it goes cosine, cosine, sine, sine, different sine, like that. All right. Okay, I promise you I haven't had a glass of wine before doing this pencast, or not pencast, this video, okay? I am doing fine. All right, so what you'd have on this is you'd have a plus sign there, so that would mean that would correspond to a cosine difference identity. So you would really be doing cosine of 165 degrees minus 45 degrees. Like that. So if you work that out, that's the cosine of 120 degrees. So it's basically, we just need to look this up on the unit circle and figure out what that value is. Okay, so on a unit circle, we're in quadrant 2. 120 degrees is this point on the unit circle. And that point corresponds to the point -1/2 and square root of 3 over 2. Okay, so the cosine, of course, is the x value. So that means the answer to this problem is going to be -1/2. Okay, now one thing that you could do on this, again, I kind of like to show the calculator a lot as a checking tool. So one of the things that we could do on this is you could put this in actually like this. You could go through and put in the problem as it is, and we'd want to be in degree mode, so you could actually go like cosine of 165, close parentheses, times cosine of 45, close parentheses, plus sine of 165, and then times the sine of 45, and get a decimal answer. Okay, well notice that's what -1/2 is. So once again, voila, the calculator shows that we're right. Okay. All right, that's not a proof, but it's a demonstration. Okay, the next problem works out basically the same way. The key thing is you have a minus sign there, which means you're going to use the cosine sum identity, like that. Now we're just going to keep this in radians, so this is going to be the same thing as cosine of pi over 5 plus 2 pi over 15. So what we need to do is we need to get a common denominator and just add this together. So 15 is the common denominator, so I'm going to multiply that by 3 over 3. So that's going to give the cosine of 3 pi over 15 plus 2 pi over 15. And that's going to give the cosine of 5 pi over 15. But that fraction reduces by 5, so we're down to cosine of pi over 3. Okay, and on a unit circle, this works like this. Okay, of course, you're in quadrant 1. Your unit circle goes like this. You have these angles. You have pi over 6, you have pi over 4, and you have pi over 3. Okay, the point on the unit circle is 1/2 for x, square root of 3 over 2 for y. So that means the answer to this problem, since we're doing a cosine of pi over 3, is the x value. So that means that answer is going to be +1/2 this time. Okay, so that's how that works out. Okay, and again, that could be checked on the calculator with a similar mechanism that I did on number 4. Okay, so I am going to pause my recording for a minute and let you work a little bit on number 6. Okay, so the way I would look at this now is, this is a plus, so that means you're going to use the cosine difference identity. So it goes cosine of the first angle, which is 5 pi over 18, minus pi over 9. Okay, so we got to get a common denominator, which is 18. So I'm going to leave the 5 pi over 18 alone. And I'm going to change the pi over 9. I'm going to get a common denominator, so I'm going to multiply that by 2 over 2. And when I get that, I'm going to have the cosine of 5 pi over 18 minus 2 pi over 18. So that leaves us with the cosine of 3 pi over 18. And that reduces down to the cosine of pi over 6. Okay? So pi over 6 is going to be, when you look at this point on the unit circle, I'll just use this up here, you have the point square root of 3 over 2, 1/2 on the unit circle. So that means the cosine is the x value. So you should have came up with the answer of square root of 3 over 2 on this problem then. Okay, just show you one more time how you could verify this on a calculator using the TI. So I'm going to put myself in radian mode since the problem was given in radians. And I could go like this. I could go cosine of 5 pi over 18, close parentheses, times the cosine of pi over 9, close parentheses, and then do the sine, plus the sine of 5 pi over 18 times the sine of pi over 9. Press enter, get that answer. Now if we take our answer, which is the square root of 3 over 2, look at that, you get the same answer, so that would verify on the calculator that it's right. Okay, so the next topic we're going to look at is what we mean by cofunction identities. So here's the key. We have a cosine, a cotangent, and a cosecant, not to be confused with codependent. Okay, cosine, cotangent, cosecant. Okay, so here's what the deal is, and it's real easy to remember, is you have this. You have the sine and you have the cosine, are called cofunctions. You have the tangent and you have the cotangent, are called cofunctions. And you have the secant and you have the cosecant, or cofunctions. So we're going to get what we call cofunction identities, which you need to memorize. But you don't want to blindly memorize them. You want to understand where they come from is kind of the idea. So what I'm going to show you on this is I'm going to demonstrate this with a triangle. So I'm going to have you maybe just draw a triangle at the side. And let's do just like a 30-60 triangle because it's pretty easy to interpret in demonstrating these identities. So let's go like this. Let's say this is a 30-degree angle, this is a 60-degree angle, and this is a right angle. And then we know the way the sides go are 1, square root of 3, and 2. Okay? So what I'm going to do is I'm going to show you, use this triangle to really explain to you what these identities are doing. So if we looked at 30 degrees, and let's start by looking at the sine of 30 degrees, okay? Based on this diagram, that would be opposite over hypotenuse, so the sine of 30 is 1/2. Now if I do the cofunction of the complementary angle, if I do the cosine of 60 degrees, I want you to notice what happens. The cosine is adjacent over hypotenuse, so it's also 1/2. So what you notice on this is the sine of 30 and the cosine of the complementary angle are the same. 30 and 60 add up to 90, so they're called complementary angles. And it'll work the same way for all of these. Let's go with the tangent of 30 degrees. Okay, the tangent of 30 degrees, by definition, is opposite over adjacent. So that's 1 over square root of 3. And I'm not going to bother rationalizing that because it doesn't matter. I'm trying to show you a point anyway. Now, the cofunction of the tangent is the cotangent. And let's do the cotangent of the complement, 60 degrees. So if we go to 60 degrees, the cotangent is adjacent over hypotenuse. So it's the same thing. So again, what I'm trying to show you is the tangent of 30 and the cotangent of its complement are the same thing. And that's what these identities are going to say. And then let's do one more. Let's do the secant of 30 degrees. And let's compare that to the cosecant of the complementary angle, 60 degrees, and let's see if they're the same. Okay, so the secant of 30 degrees, by definition, is hypotenuse over adjacent. So that's going to be 2 over the square root of 3. The cosecant of 60, its definition is hypotenuse over opposite, so it's also 2 over the square root of 3. So again, what I was trying to show you on that is the secant of 30 and the cosecant of its complement are the same. That's what cofunctions are. So when you build these identities, now these identities are written in radians, this is kind of what you're doing on this, okay? When you look at this identity right here, this is also can be thought of as saying the sine of 90 minus u. Well, the thing is that's how you find a complement. If you know 90 minus 60 is 30, see? Okay, so it goes like this. So the way that you come up with these identities, this is really just saying the sine and cosine are cofunctions, and then angle u, you want to find its complement by subtracting it from 90. That's what that's saying. And then this identity is just saying the same thing backwards. And then this is the tangent and cotangent. So if you have a cotangent of u, that's the same as the tangent of the complement. So the thing that you want to understand is this thing that I'm highlighting is just a mathematical expression for finding a complementary angle like that. So one of the things that you want to be able to do with this identity is something real easily. So you can develop these identities very easily. So you have the sine, just pick an angle, say like alpha. Well, the cofunction of the sine is the cosine. The complement of alpha is 90 minus alpha. So you have an identity. You really have that version of the identity. Take another one. Take the tangent of, say, beta. The cofunction of the tangent is the cotangent. The complement of beta is 90 minus beta. And then here's another one. You could say the secant of, say, gamma. The cofunction of the secant is the cosecant. The complement of gamma is 90 minus gamma. Now, of course, you can also use pi over 2 instead of 90. So if you understand what cofunctions are, this is not a bunch of new identities that you got to remember. You just got to know what cofunctions are. Okay, now I'm going to do a little bit more of a direct proof on this next page. So, of how these identities work. So we're going to start by looking at angle u in this problem. And so if we start off with the cosine of course is adjacent over hypotenuse. So that would be b over c is what the cosine of u is. Okay, the sine of the complement, and see the complement, what I'm going to do is highlight this like this so that we're kind of we're always going to be looking at the complement. So I'm going to highlight these things so you'll kind of see what I'm talking about. And then angle u is just the original angle. And this should demonstrate and prove to you that these identities are right. Okay, so the sine of 90 minus u, or pi over 2 minus u, is going to be opposite over hypotenuse. So that's b over c. So notice the cosine and the sine of the complement are the same. If we do this backwards, the sine of u is opposite over hypotenuse, so that's a over c. The cosine of the complement is adjacent over hypotenuse, so that's also over c, so that shows that the sine and the cosine of the complement are always the same. Okay, if we go to the cotangent is adjacent over opposite, so that's b over a. The tangent of 90 minus u, or pi over 2 minus u, is opposite over adjacent, so that's also b over a. The tangent of u is opposite over adjacent, so it's a over b. The cotangent is adjacent over opposite, so that's also a over b. And then the same argument goes for the cosecant. The cosecant of u is hypotenuse over opposite, so that's c over a. The secant of the complement is going to be hypotenuse over adjacent, so that's also C over A. And finally, the secant of U is hypotenuse over adjacent, so that's C over B. And then the cosecant of the complement is hypotenuse over opposite, so that's C over B. So what that does is that shows you and kind of gives a proof that these things are going to work out. Okay, so here's one of the ways that you use this. If you have the sine of 30 degrees, okay, that means it's going to be the same as the cofunction of the complement of that angle. Okay, how do you find the complement of that angle? You do 90 minus 30, so you get 60 degrees. So the sine of 30 and the cosine of 60 are the same. Okay, same thing applies to this. If we do the tangent of 10, that should be the same thing as the cotangent of the complement. The complement of 10 degrees is 80 degrees. So tangent of 10 and cotangent of 80 are going to give the same answer. And then finally, you have the secant of 89 should be the same thing as the cosecant of the complement. The complement of 89 is 1 degree. So that's what you have. So one thing you could do, with a calculator, it's pretty easy to demonstrate this. If I was to put my calculator back in degree mode, it's actually very easy to demonstrate all this stuff. So if we did the sine of 2 degrees, we get an answer. If we do the cosine of 90 minus 2, we get the same answer. Okay? If you did the tangent of 5 degrees, you get an answer. Well, if you do the cotangent, now you have to go, to do a cotangent, you have to go like this. You have to go 1 over tangent. Well, the complement of a 5 degree angle is an 85 degree angle. So you get the same answer. And you'd do the same logic would apply always on those. Okay? All right, now moving down just a little bit here, we're going to do a few problems to finish up this page. So if we're going to do number 8, first of all, the cofunction of the cosine is the sine. So we need to do the complement of this angle. So the complement is always found by subtracting from 90 degrees or pi over 2. So I'm going to use pi over 2 and keep this in radians. So I need to get a common denominator, which is 24. So I multiply by 12 over 12. So that's going to give the sine of 12 pi over 24, which of course is pi over 2, minus pi over 24. And that's going to be equal to the sine of 11 pi over 24. Should be an answer to the problem. And there's nothing to that, but you could quickly check on your calculator if you wanted to. Okay, that's always a good thing to demonstrate. So I'm back in radian mode, I think. Okay, so I could go take the original problem, which is the cosine of pi over 24. And that would give me an answer in decimals. And then if I did my answer, which is the cofunction, sine of 11 pi over 24, that should give exactly the same answer, and it does. So that's how that works. Okay. Next problem is going to work like this. The cofunction of the tangent is the cotangent. And then you need to do the complement of that angle. So you're going to subtract 28 from 90. So that will give you the cotangent of 62 degrees being the answer to that problem. Okay. So what we've done on that is we've just showed that the tangent of 28 is the same as the cotangent of its complement. Okay, so let's pause. I'll give you a few minutes to work. Okay, so I'm going to see if you got these okay. So it's all pretty simple things to do. So the cofunction of the sine is the cosine. And then the complement of 81. Now you can do that in your head, but that's going to work out to be the cosine of 9 degrees. So what we showed is the sine of 81 and the cosine of 9 are the same thing. 81 and 9 are complementary angles. Okay, on the next problem, the cotangent, the cofunction of the cotangent is the tangent. So we're going to do pi over 2 minus 17 pi over 18. Okay, to get the complement, we got to get a common denominator, which is 18. So I'm going to multiply that by 9 over 9. And that's going to give the tangent of 9 pi over 18 minus 17 pi over 18. Okay, when we work that out, that's going to be the tangent of negative 8 pi over 18. And then that fraction can reduce by 2 to give you the tangent of negative 4 pi over 9. And that's the answer to the problem. And it is okay for it to be a negative answer. Okay, there's no law that says these things can't be negative answers. They certainly can. So those two things would be the same. Okay, and notice like on the calculator on this one, I'm in radian mode, so you could go like this. You would actually put in 1 divided by tangent of 17 pi over 18. Of course, that's how you have to put the cotangent in. Then take our answer, which is the tangent of negative 4 pi over 9, and that'll give the same answer. So it's 100% checkable. It's not really that big of a deal to find a cofunction, but it's verifiable on a calculator. Okay, now, these kind of problems are analytical problems, which are kind of good to go through. You're given two pieces of information. First of all, you're given the cosine of A is a third, and you're given that angle A is in quadrant 1. You're given a second piece of information. You're given a sine of a different angle. Angle B is negative 1/2, and you're given angle B is in quadrant 4. Your job is to find cosine of A plus B. Okay, so the first strategy on this would be to write down the identity for the cosine of A plus B. You aren't going to get anywhere else on this problem unless you use the identity. So we're going to say cosine of A times cosine of B minus sine of A sine of B. So we're going to write down that identity. Now, one thing I want you to notice on this is the cosine of A, you were given that. Okay, so that means that you can just replace the cosine of A with 1/3. You were also given what the sine of B is. So that can plug in here. So the sine of B gets replaced with negative 1/2, and that leaves you to work with figuring out the cosine of B and the sine of A. So if you can figure those two things out, then you'll have a solution to the problem. So what we're going to do is we're going to do a couple of unit circle diagrams. I'm going to start by just kind of considering this angle A. Angle A is in quadrant 1. So if we're in quadrant 1, let's just draw a picture of a quadrant 1 reference triangle. Now you were given the cosine of this angle A, which is in quadrant 1. You were given that that's 1/3. That means that X is 1 and R is 3. So I'm going to just label this as 3. That is 1. Then you'd have to find Y by doing the Pythagorean Theorem. Okay? So you could do this like this. You could just do the Pythagorean Theorem. So we have X is 1. So we'd have 1 squared plus Y squared equals 3 squared. So that's 1 plus Y squared equals 9. That's Y squared equals 9 minus 1. That's Y squared equals 8. Then if you do the square root, you get Y is equal to plus or minus square root of 8, but I can break that down like that to get 2 radical 2. Now that is a positive value since we're in quadrant 1. So we have that. Okay, now we need to find the sine of A. Okay, the sine of A comes from these things. Here's angle A. The sine is Y over R. So that means it's 2 root 2 over 3. So I'm going to plug in for sine of A what it's equal to. It's equal to 2 times the square root of 2 over 3. Then we'll work that out. Now the next thing we're left with is finding the cosine of B. So we really need to make a separate diagram on this when we solve this. Okay. So what I'm going to have is, this time it says that we're in quadrant 4. So I'm going to draw a picture of a quadrant 4 angle, and I'm going to use a reference triangle to show that then. And again, what you're given on this is you were basically given the fact that the sine of angle B, which is this quadrant 4 angle, is equal to negative 1/2, which means y is going to be negative 1, and that means r is going to be 2. Okay, now you can do the Pythagorean theorem to find x, but actually x is going to work out to be positive square root of 3 because you have a special triangle. Now when you find the cosine of b, the cosine of b, this angle b, is x over r. So that means cosine of b that we're going to fill in here is going to be square root of 3 over 2. Okay, so now we've got all the information we need to solve the problem. Okay, cosine of a was given, sine of b was given. The other two things we had to reason out. Okay, so when we multiply straight across, you're going to get square root of 3 over 6 there, minus, and then this is going to be a negative 2 root 2 over 6 when you multiply that straight across. The subtracting a negative is adding, so you'd really have square root of 3 over 6 plus 2 root 2 over 6. So that's going to give an answer of square root of 3 plus 2 root 2 over 6. So that will give this final answer of the problem. Okay, like that. Now what I want to show you is how we could use a calculator to verify this answer, because it's actually not that hard to verify this on a calculator, but you do have to work a little bit with inverse trig functions to do this then. So what I'm going to do, I think you'll probably see it better if I'm in degree mode, so I'm going to put myself in degree mode when I do this. Now I'm going to do the inverse cosine of A. So I'm going to do second cosine of 1/3. And that'll give me what angle A is. Okay, so angle A is about 70.5 degrees. I can also find angle B by doing the inverse sine of negative 1/2. That'll give me a special angle, I think negative 30 degrees. Okay, so it gives that. So that would mean then that angle A is 70.5, angle B is negative 30 or 330. Okay, you could take negative 30 and add it to 360 and get 330. Now in this problem you were supposed to find the cosine of A plus B. So you could go cosine of this answer, which is 70.52877, 937, plus, and I'm going to use, instead of negative 30, I'm going to use 330, although it doesn't matter. So we're finding the cosine of the sum of those two angles, so we get this answer. Now if we take our answer and plug it in, we would go square root, parentheses, square root of 3 plus 2 times the square root of 2, double up on the parentheses, not triple up on them, double up on them, divide by 6, you get the same answer. So the calculator can verify that you have a right answer on this problem too. Okay, right? So that's how you would do that, is you would have to find the inverse cosine of A, the inverse sine of B, then take the cosine of the sum of those angles, and then compare that to your answer. So it's verifiable. All right, so I'm going to give you all a chance to work out one of these problems, just number 13. Give this one your best shot and see how. Okay, so let's see if we got this figured out. This problem's got a lot of reasoning on it. So the first thing is you're going to figure out the cosine of A minus B. So you want to start the problem probably by writing down the identity, okay, for cosine A minus B. So that's going to go cosine A, cosine B, plus sine A, sine B. Okay, now in this particular problem, it looks like you were given two things. You were given the cosine of A, all right, so you can plug that in as negative 5 over 13. You were also given the sine of B, so we can plug that in, and that's going to give 8 over 17. So that's going to mean in this problem that we got to find two things. You've got to figure out what the cosine of B and what the sine of A is, And those things are going to come from the information that you're given. Now, it did say that both angles were in quadrant 2. So what I'm going to do is just make a diagram for each angle. So let's start with a quadrant 2 angle for angle A. Now, these angles are different. So I'm going to make a angle. This is going to be my angle A, and it's going to be in quadrant 2. Okay. Now, notice I was given this. I was given the cosine of A equals negative 5 over 13, which means that I gave you x, and x is a negative value, so that's negative 5, and it also means that I gave you r as 13. Well, y would be 12. You can get that from the Pythagorean Theorem if you want to. Okay, so that means we have to find the sine of A. If we're doing the sine of A, we're doing two things. The sine of A is going to be equal to y over r, so that's going to be 12 over 13. So that gets plugged in with 12 over 13 as the sine of A. Now we got to build a new angle. We have to really do a new angle diagram. So I'm going to go over here and make a diagram for angle B. And this is going to go like this. Again, we were told that it's in quadrant 2. So this is my angle B. Draw my reference triangle. Now the key thing is that you were given in this problem that the sine of B is 8 over 17. So that means y is 8. So that's that side of the triangle. R is 17. Then you got to find x. So what you do is Pythagorean Theorem. So you'd have x squared plus y squared equals r squared. So that is x squared plus 64 plus 289. So that's x squared equals 289 minus 64. So that's x squared equals, I think, 225. And then if I square root both sides, I get x equals plus or minus 15. But since you're in quadrant 2, x is to the left, so that's negative 15 then, like that. Okay? I did that in my head. I want to make sure I did that right. So 8 squared plus 15 squared. Yeah, that's right. Okay? All right, so now we go back. We've got to find cosine of B. Okay, well, the cosine of B is x over r. So that means cosine of B is going to be negative 15 over 17. So now we are ready to crunch this sucker out. Okay, multiply those fractions together. So negative 5 times 15 is negative 75. 13 times 17 is 221. Okay, then we got these fractions. We got 12 times 8 is, I think, 96. And then that's over 221. Okay, just combine it into one fraction. So 96 minus 75 is going to be 21. So it looks like the answer to this problem is 21 over 221. Like that. All right, well, let's do a quick little check on the calculator. I would like to show you guys how to do that again. So just one more time. Doing that. Okay, I'm going to go with degree mode on this one. So I can actually find A by doing this. If I do the inverse cosine of negative 5 over 13, I'm going to get a 112 degree angle. Now that is quadrant 2, like it said. And then if I do, now you got to be careful about this. If I do the inverse sine of 8 over 17, I'm not going to get a quadrant 2 angle. I'm going to get a reference angle. So I need to take 180 minus this angle. I'm going to use the answer key. So it's 151. Okay? So what you would end up kind of doing on this problem then is you'd have to do this. You're doing the cosine of A minus B. So you would have to do the cosine of angle A, which is 112.6198,649, and then minus that angle B, which is 151.6198,649. And that gives that. If I did my calculations right, that is. I'm not sure if I did my calculation right on that or not. Okay, I think I did though. And then that doesn't look right. That's 21 over 221. So I'll have to double check that. Let me pause this and check this first. Okay, so I just caught my mistake. And one of the reasons I like to spend a little bit of extra time going over this stuff too is to show you how I catch mistakes. So my mistake was cosine of B on this. So the cosine of B is this angle over here would be negative 15 over 17. So that should have been right here. That should have been a negative. So that would make that a positive 75. Now we get a lot more logical answers. So if I go 75 plus 96, this is 171. This is what we would get here. So let me change this answer then. So that is going to give 171 over 221 as an answer of the problem. And that does match up with what my calculator was showing, I think, okay? So if I do, see I had 0.77, but if I do 171 over 221, then I think that'll match up okay. So that's definitely right. Sorry about that. Hey, that's one of the reasons I like to show people about checking answers, because you can do that. Okay, let's finish up the section then with just a couple simple things. We can use the cosine difference identity on problem 14. So I'm going to write this as cosine of 90 degrees times cosine of alpha, different sign, plus, and then do sine of 90 degrees times the sine of alpha. So you can use cosine identity to work this out. Now, if you look at 90 degrees on a unit circle, you're looking at the point 0, 1. So that means the cosine of 90 is going to be 0. And then the sine of 90 degrees is going to be the y value, or that's going to be 1. So you'd have cosine of 90 is 0. It's going to cause a cancellation. Sine of 90 is 1. Okay, so this ends up giving 0 plus sine alpha. So that will give sine alpha. So what we just showed is the cosine of 90 minus alpha is equal to the sine of alpha, like that. Okay. Now, one thing that I like to show on this problem with a graphing calculator that's kind of a decent thing to show students is, let's say I'll keep myself in degree mode on this, and I'll just do a graph. I'm going to do a graph of these two things and show you what this means graphically. So I'm going to take off what I have in here, and I'm going to do this in degree mode just because that's 90 degrees. So I'm going to put in cosine of 90 degrees minus x instead of alpha. And then for my window, I'm going to go 0. Since I'm in degrees, I'm going to go 0 to 360 by a scale of 90. And I'm going to go negative 2 to 2. Okay. So this is the cosine of 90 minus alpha. You have a phase shift. You also have a reflection over the y-axis on that as well. Well, I want to show you something. If I put in the sine of alpha, well, I really don't need to do that. If you look at this graph, doesn't that look like the sine wave? Starts at 0, 0? Of course it is. So it's the same. So this graph is the same as that graph. So that's kind of a good thing to show. Okay, so I'll let you all do 15. All right, what you should have came up with on this one is, first of all, you should have used the cosine difference identity. So you should have done cosine of the first angle times the cosine of 270. Don't put a negative in there. I always see students put negative angles. No. That's a part of the identity. That just tells you you're going to have a plus sign there. Then you do the sine of alpha, and then you do the sine of 270. And then you got to work it out. The rest of this is just looking at what's going on at 270 on a unit circle. On a unit circle at 270, you're looking at the angle negative 1, so that means the cosine of 270 is 0, and it means the sine of 270 is the y value, it's negative 1. Let's just crunch out the details. So this is going to be cosine of alpha. Cosine of 270 is 0. Then you got sine alpha, and the sine of 270 is negative 1, so this is 0 really minus sine alpha. So the answer is going to be negative sine alpha. Okay, and that will be the end of this section. So we just showed that the cosine of alpha minus 270 is the same. Negative sine alpha, you could check that graphically. They would have the same graphs then. All right, so that will be the end of this section. Hopefully this brought a smile to your face, as all this trigonometry stuff does. It's good stuff. So hope you enjoyed the video and hope you learned a lot.